So let's take a look at the case that we have, for example, an x to the n, the nth derivative of y plus an minus 1, x raised to n minus 1, y to the nth minus 1 power, plus the middle terms, and finally we have a1x, the first derivative of y, plus a sub 0y equals to g of x. First of all, this differential equation is called Cauchy-Euler equation. To solve these types of differential equations, we're going to use y equals to x to the n. You start taking the first derivative, the second derivative, and the third derivative of x to the n, and then we substitute that to the homogeneous part of the differential equation and try to come up with the complementary solution. Well, let us focus on the second order differential equation of Cauchy-Euler form. Let's start by working with the first example. This example says, solve the following differential equation. We have x squared, the second derivative of y, minus 2x, y prime, minus 4y equal to 0. So this is a form of a Cauchy-Euler differential equation. We're going to use y equals to x to the m. Y prime is m, x to m minus 1, and the second derivative is m minus 1, x to power m minus 2. We're going to substitute them into the differential equation and form the auxiliary equation. We get x squared, parentheses m minus 1, x to m minus 2, minus 2x times y prime, which is m, x to m minus 1, minus 4 x to the m equal to 0. As you can see, you can factor out x to the m, and we end up with m squared minus m minus 2m minus 4 equal to 0. Our auxiliary equation becomes m squared minus 3m minus 4 equal to 0. So we're looking for two numbers that their product is negative 4 and their sum is negative 3. We get m minus 4 times m plus 1 equal to 0. As you can see, we have two distinct solutions. M is 4 and m is negative 1. Well, the solution can be written as y equals to c1 x to the 4th plus c2 x2 minus 1. So in general, if m1 and m2 are distinct solutions, the general solution can be written as c1 x to m1 plus c2 x raised to m2.